really how you to come up with different ways of doing AI besides just doing something on the computer. Okay, so so the idea is to actually try to do AI more like the way the brain does it, but the brain is not hooked up to a computer. So can you have a system that's not hooked up to a computer that can still learn AI sorts of tasks? But before I do that, I just want to mention tomorrow afternoon, I'll be moderating a human rights session, a session on current issues at the intersection of science and human rights. There are many of them. And I'm actually vice chair of the Committee for Human Rights in the National Academy of Sciences, National Academies of Sciences, Engineering, and Medicine. It's such a mouthful. And this is just a QR code to the website for ways to promote human rights. But this is not what I'm going to be primarily focusing on. Really, I wanted just to have a discussion. We'll just have a few introductory remarks suggesting actions that people can take right now. Okay, so why would you want to do AI without a processor? To think about that, let's just think a little bit about the differences between an artificial neural network and a real one. An artificial one uses gradient descent, some form of gradient descent on a cost function, right? And that really requires knowing everything, all the details about the network. And then to take a step of gradient descent, that requires a lot of computation, right? So this really, we need a processor. The brain, on the other hand, the neurons update by local rules. So there are many of them. And one example is, the famous Hebbian rule of neurons that fire together, wire together. Okay, but there are many things to control them. And it doesn't obviously require a processor. We are not each hooked up to a computer. So what are the advantages of learning by local rule versus learning by gradient descent, some form of gradient descent? Well, I think the most obvious one is energy efficiency, right? So I don't know that if you know that a ChatGPT query for just 100 words, okay, costs 1/4 of the amount that our brain uses an entire day. Okay. So, and an image, okay, takes 5 times more, okay, than we use an entire day. So that's just the electricity. That's not counting, the cooling water, okay, or any of the other costs associated with this. This is just the electricity to run the model, okay. It's not free. We use it as if it costs nothing, but it's actually a serious problem. And it's running into a wall. Okay, that's why Microsoft is thinking of opening up Three-Mile Island, or is planning to open up Three-Mile Island and stuff like that. It's because it just takes so much energy. I'm sure you've read all about it. Why is that? Well, for one thing, it's digital, right? Brains are analog. A big thing is the von Neumann bottleneck, that every time you do an operation, you have to, for example, suppose you want to add 2 numbers, you put the first number in memory, okay, you want to add you have this second number, you have to take the second number out of memory, bring it back to the processor. And that's called the von Neumann bottleneck, just shuffling things in and out of between the memory and the processor. And that's the needed both for inference and for training. And the brain, suppose it's doing something that it already knows to do, right? Its connections are already there, okay? And where are they? For example, when the wired together, they're in the synapses, okay? The memory is right there where the computation is taking place. There's no bottleneck. And the same thing with learning. You create synapses, okay? For example, or print them away. that's done right where that process is done right where the memory is, because the memory is in the state of the synapse, for example. There are also lots of differences, because back propagation is such an efficient, is the efficient algorithm, right? That means that networks have to be primarily feed forward. Brains are actually highly recurrent. And there's evidence that that really helps learning. Okay. I don't know why, networks require so much data, whereas, the brain doesn't necessarily require so much data to train. Okay, but that certainly, it has been a problem for neural networks. And, because they're digital, right? They're very precise, and that precision is really needed for doing something like gradient descent, because arrows can propagate, right? Backwards when you do your back propagation. So it needs to be very precise. Because the brain learns by local rule, okay, it can get away with being having much less precision. It's also very slow, okay, compared to the time that it takes to flip a bit, which I think is about a femtosecond. Here, this, of course, if we're dealing with analog data, we need to convert that to digital. That's also expensive. So, having a local rule, analog system during a local rule makes processing analog data very natural. I already mentioned these other things. The other thing is, of course, this can be parallelized, and that's, of course, what we all do, but this is automatically parallelized when all the, synapses are updating at once, right? Following their own local rules, that's automatically parallel. Okay, so local rules are inherently parallel. So what we have done, and this is mainly work done by my collaborators, Sam Dillaboo used to be a postdoc working with Doug Durian and me. Doug Durian and Mark Miskin at Penn. They're the ones who have implemented this thing based on a local rule I'm going to tell you about that was developed by my former postdoc Matthew Stern, now to Emil. So the idea is they're analog, okay? They do supervised learning, so they're effectively performing gradient descent, but using a local rule to do it, okay? The memory in this case, if I just think of an electrical network where every edge of the network is an adjustable resistor, okay? Then the memory is in the resistor, okay? The state of the resistor. And that's where the learning happens, because that's where you adjust the resistance, okay? And that's also where the computation happens, that you feed it voltage inputs and you get desired voltage outputs, okay? So, so it's in memory, compute, and learning. As I said, because it's a local rule, it's parallel, and it's as recurrent as you want it to be. A resistor, for example, is completely recurrent, right? It's bidirectional and symmetric. Okay. I want to point out, it doesn't mimic the brain. It's totally different from electronic spiking neural networks, okay, that try to actually mimic the brain and make rules that when they spike together, they wire together with transistors. Okay, so it's not mimicking the brain at all. It's using a physical process of power minimization, okay, and a local rule that's enabled by physics. So it's physics based. It's not biologically inspired. So here's the way it works. Okay, so I just want you to think about the simple case of resistors. So usually we have a cost function which says, okay, suppose I have sources, okay, voltage inputs, for example, and I want a desired voltage output. Okay, so that's how I'm going to feed in my data. Okay. The cost function says that here at my output, okay, I want the free response, which is when I just apply the source and let the network be free to give me what it wants, okay? I want that free response to be equal to the desired response. So I take the difference and I square it so that it's positive, and then I minimize this with respect to my tunable parameters, which in this case are the resistors on all of the edges of this network. Okay. We're going to replace this by a set of two different boundary conditions, a contrast function, where this system, because it's an electrical network of resistors, it wants to satisfy Kirchhoff's law at every node. Okay, no net current at every node. Okay, that's equivalent to minimizing the power. Okay, so what we're going to do is we're going to say, well, what we want is the power that's minimized under conditions where I just have the free case where I just applied the inputs, okay, and let the outputs be free to be what they want. I want that power to be the same as when I have the desired target response, right? I want the free state to be the same as the clamp state where I not only apply the inputs, but I apply the desired outputs. Okay, if these two are the same, then I've got the response that I want. Okay. Now, the great thing is that physics tells us that this is already positive or non-negative. Why? Because if I took this off, the system would go right back to this to minimize the power. Okay. So dragging this away from where it wants to be by applying the desired outputs has to give me a larger power, and they're equal when they're the same. Okay. So the great thing about that is I don't have to square it in order to minimize it. Okay, now what are the consequences? Well, if I now take a update on the conductance of edge I, okay, to follow the gradient of this difference, what you can see is that in the end, right, all that's left for the update on edge I is the voltage drop across edge I under the clamped boundary condition minus the voltage drop. Oops, I'm missing a square there. In the free voltage drop squared in the free case.
Is K the resistance?
K is the conductance. I'm sorry. K is the conductance. Okay. So if I take the derivative of power with respect to conductance, right, I can go to the voltages. This is minimized. Okay. The power is going to be at a minimum with respect to the voltage. Why? Because I want to satisfy Kirchhoff's law. Okay. And so that term drops out. This is just update Ij. Okay, so that just gives me that. So this is a local rule that the update to conductance I just depends on the voltage drop across edge I. Doesn't depend on the other edges. Okay, you see that if this were squared, if we had to square that, we'd get cross terms and it would not be a local rule. Okay, so it's really essential that we don't have those cross terms. Okay, so this was the brainwave of Nachtwey-Stern. Okay.
Excuse me, but
Yeah.
how is the information about how it's communicated to a given resistor? Because in some sense, like if you're doing a supervised task, right, you present the input and then the network produces something that you have a desired output. So I can see that by differentiating the power, you get something like the one that you have. But like what I missed is how is the output communicated to that resistor?
It's communicated through Kirchhoff's law because the current has to be zero at every node, right? So that's how this local rule gets communicated to the collective scale, because in fact, the voltage drop across one edge is connected to the voltage drop across all the other edges. They're related because the whole system has to satisfy power to be at a minimum of the local power.
Yes, like what I don't understand is how do you run this system? So you have your network, it's electric circuit, right? So you present an input, presumably the inputs are encoded by some current or voltage or whatever. Then you run, right? So essentially every element within the network requires certain state.
That's right.
So that's the free path. And
That's right.
And then
in the clamped one, you apply not only the inputs, but you apply the desired outputs. And there's a caveat here. You actually don't apply the desired output right away. You sort of take the output that you get in the free case and nudge it towards the value that you want. So you do this gradually. Okay. So So, okay, but essentially you apply the output that you actually want. Okay, and then you do this update based on that.
But in order to frame it, you need to alternate between the two phases. So
Yes,
so
I'm
you
getting to
constantly
that.
Go back and forth.
How do you do that? How do you do that? Because naively, you would have to stick. You cannot run two boundary conditions at the same time, just as you pointed out. So if you do the clamp, then you have to put it in memory, and then you do the free, you have to take it out. So how do you get around that? I'll explain that. Yeah, I can.
Can you remind me, is there an assumption about constitutive relations of how your system responds? Is this rely on the constitutive relation being linear, or is there a general version
For an
of
IV
this?
curve, yeah, you can generalize this for a nonlinear IV curve.
It's the same way.
Yeah,
The
yeah,
operation-
same.
Operationally, it would be there.
Operationally, it's very similar. Yeah, and it's still a local rule. Yeah, even if you have a nonlinear IV curve. Yeah, you're still minimizing something to get up to satisfy Kirchhoff's law in every node. Yeah. Oh, I had animations here. I forgot. Okay. Nudging. Okay, we got through all that. Okay, so it's like, okay, if you do this on the computer, right? Remember, there are really two things going on here. We're trying to minimize this cost function or the contrast function instead, okay, by adjusting our conductances, right? And so we're replacing gradient descent with this local rule for my tunable degrees of freedom, which are the conductances. But at the same time, the system has to be at a power minimum, physics says so, okay? And that's a first optimization, that I have to minimize the power with respect to the physical degrees of freedom, which are the node voltages. And these are coupled together, okay? So it's really what the system is doing in order to make this work. It's a double optimization process, okay? You can see that if you do this on the computer, that's fine, it's cool, okay? But you still have, you can do this, you can get rid of gradient descent here, but you still have to minimize the power, okay? So like, well, that's no good, okay? That's still global, it requires a processor to do it, okay? But here's the thing, that if you do it in a real system, okay, physics will do that for you automatically. You just apply the inputs and physics will calculate the outputs for you. Okay, so so that's why it has to be done in the lab. Okay,
As an abstract problem, how hard is it to minimize power in an artificial sense?
well, for a nonlinear for a nonlinear IV curve, it's actually a pain. How many points can tell you? It's a pain. Okay, linear case, it's just matrix algebra. It's just linear algebra, but otherwise it's a pain. All right, so just for the first generation networks, okay, you can buy these variable resistors, okay, but then you're left with this problem that was just pointed out, which is how can you compare the voltage drop across this edge under two different boundary conditions when you can't apply them at the same time without using external memory or processor. And so the solution, okay, that they came up with is to have twin network, identical twins, okay? So one network, and they sit right on top of each other. So each edge is really two edges, okay? So this is the first generation, and here's an edge, it's both on the breadboard, and it's got the 3 variable resistor and the clamp variable resistor all there. So it's really two edges, okay? When you update one, you update the other, and then there's just some circuitry that compares and clicks the resistance of this variable resistor up or down depending on the sign of the voltage difference across those two, okay? So that's how the first one worked. All right, so and this could do things like classify the iris data set as well as any linear classifier could do.
I don't think we can kind of conquer this whole discussion, but I still don't quite understand what is happening. So you have three methods, you have two calls, right? So you run one using the
Three.
class, the other one using the plan
Plan.
class or notch class.
Right.
And then you compare the voltage drops across the two and you teach it and communicate it with the user.
It requires just a little,
So it needs to be a computer. With system.
no, it's just some circuitry. In fact, now we do it all with transistors. It doesn't
There's
require,
some additional circuitry that.
there's
comes
just some
with the
additional,
filter
yeah.
And adjust those values.
It can be done, for example, with a little logic gate.
Okay, fine, but then there's the next question.
Sorry,
let's-
she only has about 8 minutes. It's super.
Okay, I'm glad, no, I think that this is important for people to understand it, so, okay, all right. The second generation, I just want to say, is now using transistors, and so it can be microfabricated. This was based on a design by Mark Miskin, my colleague in electrical engineering, and here it is, now bigger, 32 edges. It can do things. This is nonlinear, and so you can see that, for example, it can learn a nonlinear regression problem where it needs to put a curve to these points. Okay, it's curved. That shows it's nonlinear. It's interesting. It learns actually the moments of data in order. First the mean, and then the slope gets the slope right, and then starts curving, if you noticed. It's really robust to defective edges. Okay, so we could tear out. So Sam just went in there and he tore out this edge. Okay, so it learned the thing. Then he tore out this edge. Okay, it learned it again. He tore out that edge. It could learn it again. Tore out that edge. It actually made no difference. Okay, so you could tear out about a third of the edges and it could relearn. It's sort of like, this is a great thing about brains, right? They can actually recover from damage. And that requires, having this local rule. I just want to say that Marcelo Guzman, who's here, postdoc in my group, came up with a way to map the restricted Boltzmann machine onto these very similar circuits. Okay, so the idea is that you have an Ising model, right? And you want to adjust the couplings, which I don't know why they call them Wij instead of Jij. Okay, you want to adjust those things so that the probability distribution of the training input over the training inputs is the same as the probability distribution of your Ising model. Okay, which means that the training examples have to correspond to lower energy states of the Ising spin glass. Okay, if you want the two probability distributions to be the same, you can minimize the cross entropy. And what that gives you, I just want to show you, right? In the restricted Boltzmann machine, you get a local rule, okay? That the weight update for Wij depends on the derivative of the energy with respect to that weight, okay? And that just depends on the average over the spins that are connected to that coupling, spin I and J. So this is in fact a local rule. And if you look at this looks a lot like this one, okay? For environment and model, plan 3, these are two different kinds of boundary conditions. Boundary conditions where you apply training inputs, boundary conditions where you apply noise, okay? So this looks very similar, and Marcelo and Simone Chiarella took advantage of that, okay, to make some modifications to the twin network design to implement the restricted Boltzmann machine on the computer. Okay, and it works quite well. It can do reconstruction. So this is the original. This is showing during training, how the reconstruction improves. It can generate very reasonable digits. This is all on the computer. This is not in real life. Okay, what do we have in real life so far? We have breadboards again, that Lauren Altman, who is a postdoc with Doug, is building. It's a very simple Boltzmann, restricted Boltzmann machine with 2 input nodes and 1 output node. So all it does is invert data that you give it. Okay, but it can't do that. And it shows some nice features that you would expect to see for a Boltzmann machine. I want to get to scaling up. How am I doing? Okay, so the fact that these things are so robust to damage is really good news for making it scalable, because they just learn around problems. Okay. The current power consumption for the 2nd generation built on breadboards, okay, is 10 picojoules per parameter per inference. And that's already actually within striking distance of the most energy efficient AI chips, which use 1 picojoule. But that's not trying at all. That's on breadboards. Okay, as you shrink this down to chips, of course, it gets much more power efficient. So in terms of energy efficiency, this is very promising. So we have a few printed circuit boards that keep filling with it, making better. The new ones can do batching and so forth. There's a 3rd generation design by Mark Miskin that uses subthreshold transistors, which can, in the subthreshold regime, you can just do a nonlinear mapping and it becomes a linear resistor network again. So, we don't know how well things will scale up, but if they do scale up, the nice thing is that it requires so few electrical components per parameter, okay, per edge, that we can get with, typical microfabrication technology, we can get up to 1 billion edges on a chip, okay, and potentially reach several orders of magnitude better than the current state of the art in terms of energy efficiency. So that's what's driving us. But there are a lot of open questions. What kind of tunable nonlinear IV curve for the edges what kinds of tunable IV curves do we want that would actually give us, good learning? Klein, who's right there, is thinking a lot about. Also, what kind of network architecture would be best? We're not wedded to a layered feed forward architecture that's imposed by back propagation. Okay, so it doesn't have to be that. What should it be? To what extent do we want to have recurrent, bidirectional edges versus feed forward edges? That can be tuned in these systems. So there are many, many questions that we have to sort of think of from scratch, but I think that are very, very interesting. So just want to leave you with the people who did the work.
Amazing job staying on time. Sorry, maybe a couple more questions.
So is this something where you have to figure out like a new way for every problem that you want to approach with this? You have to figure out a new way to train the thing, or is it very general in terms of
No, for every supervised learning, it's the same. It's the same rule, because this rule just approximates gradient descent.
that it's
So
totally general?
it's totally general. For supervised learning, it's totally general. If you want to now do something like a restricted Boltzmann machine, then that's different. Okay. My collaborator, Mark Miskin, now has a way of doing diffusion models. Okay, so that, again, that's, when you do these things, that requires something different, but just for straightforward supervised learning, it's all the same.
Anything that a traditional neural network could do, this could do.
Yeah.
Presumably with much less energy.
With much less energy, but it could do more.
And
It can do more because you can do highly recurrent neural networks that right now it's just too expensive. It takes too much competition. So that's what I think is exciting. that you could actually do better than current potential.
It makes me wonder why we didn't start with this in the first place.
Yeah. And the other thing I want to point out is that doing this in real life, right, is going to be much faster than doing it on the computer, doing the same thing on the computer, right? Because in real life, this doesn't work. There's so much work.
Question about work. Yeah, so this last 2024 April regression. that you've shown.
Oh, yeah, the nonlinear one.
Yeah, what kind of nonlinearity?
Well, yeah, it's not very nonlinear. So it's just depending on, it's just a transistor. So at high gate voltages, it's quite linear. Okay, and then just by changing the gate voltage, you're just changing the resistance. Okay, but at low gate voltage, where it starts to be, you start to get close and below threshold for the transistor, then it becomes.
So it's there's a threshold line.
Yeah.
Go ahead.
So, like this chip that you demonstrated, so like when you put that architecture on the chip, do you assume that the network is fully connected? So does it have some expression of my speed?
Yeah, so that's really the question. What should the architecture be? So the initial design for the second generation on linear ones was just a square lattice. Okay,
So
Just
only
because
nearest
they're
neighbors
physicists.
are connected.
but what?
Only nearest neighbors. are
So it's only nearest neighbor, that's clearly bad. And Adam has found, Adam Klein over there, has found that, for the linear ones, the best architecture is really layers. One usable with the input layer and the output layer with all in this connection to all of that. So the standard thing, okay, is actually gives the best result.
In some sense, it's challenging to put too many wires on the plane, right? That's the biggest problem.
Oh, well, so that this all to all and this to all of this is actually pretty easy. It's done using what's called a crossbar array.
All right, let's, thank you, very good. So for the speakers, the idea is that please go on Zoom and I emailed, I just saw. Okay, we're going to wait. Yeah, okay, I just wanted to emphasize that would make things smoother and just share your screen. Also remember to log out because oftentimes. So I keep doing it. Okay, very good. Awesome.
All right. Okay, so hi everyone. Thanks for this event, for organizing this event. My name is Marcelo Guzman. I'm a postdoc in the group of Andrea Liu. And I'm going to talk about physical constraints on physical learning. By the way, this is my first time using Stick, so bear with me. And so what you see here at the left is one of the resistor networks that are able to learn, okay, that you just saw. This is the second generation. And the question I want to address today is how physics shapes the way this network learns, how it shapes the type of solutions it can find. Hopefully, by the end of this 30-minute talk, you are going to understand this image that I'm not going to explain yet. But just to tell you all this content, I'm going to summarize basically 2 papers that you can visit already. So, learning with physical systems, I'm going to go rather quickly with this. We have many reasons to try to study this kind of physical systems that are able to learn other than computers. And basically, one of the main questions is whether there are alternatives to this centralized and digital learning that we have with CPUs. There are many reasons to want to do this, and you already told a couple. For me, one of the most important ones, this more bio-inspired reason, is the brain, or even simple organisms, do not have a CPU, do not work like a computer. But instead, they are very distributed and working with analog signals and whatnot. There's also the practical motivation, which is, can we improve the current technologies to do machine learning? And Andrea just told you that we can do learning with these resistor networks, okay? I'm not going to go again over all the differences. I'm going to, however, highlight a less flattering difference, is that this is a new technology, So therefore, we have small systems, okay, between 10 and 100 parameters. And so the kind of tasks that we are actually solving are rather humble when we compare it to the trillions of parameters that we have with large language models, okay? So I'm going to focus on this kind of task that we know we can solve by the moment. And the other difference, which is going to be crucial for this talk, is that this is a physical object. And unlike an artificial neural network, which is virtual, I want to ask the question, how does physics constrain the learning of this system? So just to set the stage, let me introduce some definitions. And I think hopefully it's going to be easier given the previous talk. I'm going to talk about resistor networks. At each node, I will have physical degrees of freedom, voltages, okay, V1, V2, V3 that I collect into a vector V. Each link or edge is going to have these learning degrees of freedom, the parameters, the conductances. And in addition, this system is going to be externally driven at some of the nodes by external currents. So this is the language of the resistor networks. This is for physical learning, but if you want to have the dictionary here, the translation, in artificial neural networks, this could be the neural activations, conductances will play the role of the weights, and the current will play the roles of the input data. In addition, I will define the forward problem or the inference, and the inverse problem or the training. And I put these two equations. I'm going to be very generous with these equations. Basically, in the inference, is about the evolution of this physical state, which is going to evolve according to a function that depends on the state itself, the parameters, and the input current. And usually there is a time scale associated with this process. And the inverse problem, or the training, is going to be about the evolution of my parameters, the conductances. And again, there's a function that depends on all these variables, and usually the time scale of this process is much longer than the inference. And here again, let me highlight the main difference here. For physical system, these functions f and g are restricted by physical laws. For example, in a resistor network, you have to obey Kirchhoff's law. Whereas in an artificial neural network, in your computer, these are chosen. You have complete freedom to choose whatever you want because you're injecting a lot of energy and you're working with this digital logic gates. So let's begin with the forward problem in resistor networks. So just to detail a little bit more, this forward problem consists in 3 steps. In the first step, I have a network here. I have colored each edge or link according to the conductance. They all have the same color. They have the same conductance. And I apply some external current at some of the nodes. Here, I have chosen these 2 nodes, okay? And I apply current such that this voltage stays at 1 and this one at 0. The second step is that the network is going to redistribute currents and voltages until reaching the steady state. So here what you're seeing in color is the voltage of all the nodes at the steady state. And basically the steady state means running this inference process until basically it converges. Now, again, in these resistor networks, this is very, very fast. And it's way faster than the learning dynamics. So I'm going to ignore it for the rest of the talk. So I'm going to only focus on the steady state. And here's where the physical constraint kicks in. The steady state must satisfy Kirchhoff's law, all right? The current law, which says that every single node, the current in must be the current out. And at every loop, this is the Kirchhoff's voltage law, that the voltage drop across a loop, along a loop, has to be 0. Okay, so first step, second step, steady state, and third step is just basically reading the outputs. You don't need all the steady, all the voltages, but basically you need a handful of them. These are your output nodes. And so the actual outputs are going to be basically a projector Q times the steady state that you reach. And here I'm choosing 2 nodes here whose outputs are 0.5 for this very simple example. Now I'm going to simplify further the problem just to understand the role of physical constraints, and I'm going to work with linear networks. And what I mean by linear networks is simply that in addition to satisfying Kirchhoff's law, I have this constitutive relation with this Ohm's law. Basically that at every edge, the current is going to be the conductance times the voltage drop. And when we have these two ingredients, we can cast this steady state as a minimization problem. So we define the power, okay, which is the sum over all the edges of the conductance times the voltage drops. This is a quadratic form on the voltages, so we can write it down as a voltage vector times a matrix times the voltage vector. This matrix is what's known as the physical Hessian and depends only on the properties of my physical network. The conductances here, this is a diagonal matrix with all the conductances of my network. And this delta matrix is the incidence matrix of my graph. Okay, so it only considers the connectivity of my graph. And so the steady state, when you formulate it like this, is basically the minimizer of the power minus the input current, minus the constraint. And you can solve it quite easily for this linear problem. It's basically the inverse of the physical Hessian times the input current. So that's the inference process. Okay, and just one remark. Unlike linear neural networks, so first of all, this is a linear system, and therefore you see that the output is proportional to the input. Okay, but one difference with linear layer networks is that it is highly nonlinear on the parameters themselves. So this is not simply multiplying the weight matrix times the inputs. All the conductances appear on H, but you have to invert this matrix. So this is highly nonlinear on the parameters. All right. And so the physical constraint for this problem is that there's no way around this. You have to minimize power. That's the constraint on the steady state. Is there a question?
Yeah, just quickly, I'm curious if the Hessian is singular.
Yeah.
What solution is found?
Yes. You're totally right. There's a zero mode for this session. I'm going to work, I should have said this, with grounded networks. So I'm going to fix one of the nodes to a fixed voltage. So that removes the zero mode, and you can actually invert the Hessian. Or you can take the pseudo inverse. Okay, but yeah, good. So just to summarize, this is the forward problem. And just to simplify the notation, let me just get rid of this subscript.
That's basically just a statement that you put, if you know a voltage at least one spot, you should be able to figure out.
Exactly, yes. And so in the inverse problem, what you want now is to modify the conductances, okay? And Andrea already told you about this algorithm called coupled learning that's implemented in these resistor networks. Here, for what I'm going to tell you today, doesn't matter how you do the training, could be gradient descent as well. And just to give you a concrete example, let's modify the conductances to reach a desired output voltage, which is not 0.505, but it's close to 1 and close to 0. And you can run your favorite algorithm. One of the possible solutions here is the following. Is to develop a crack of very, very low conductance, basically a wall, in such a way that when you have your steady state, you have concentrated very low voltage here, very high voltage here, and each of these two nodes are on each side of the crack, therefore achieving the function. Effectively, what you're doing is to minimize a cost, to minimize the distance between the output and your desired output. And as we saw earlier, this becomes a double optimization problem. So what I want to study is what happens at the end of training. So once you have run this process several iterations, you find that the learned solutions are at the minimum of 2 different landscapes. Okay. For the inference problem, we have this landscape of the power. This is a cartoon, but of the power defined over this high dimensional space of voltages. Okay. And the steady state is the minimizer of this quantity. For the inverse problem, the training, you have, once you learn that you are at a minimum, you have the solution is the minimizer of this cost, which is a highly rugged landscape, because even though the problem is linear, it's non-linear on parameter space. So this is a nasty quantity, but near the solution, we can just Taylor expand. And here we have another Hessian, this time the cost Hessian. So we know that the physical Hessian defines the inference. So what's the meaning of the cost Hessian now? So the cost Hessian, so it's basically the second derivative of the cost with respect to the parameters, the conductance, that I'm going to evaluate at this learned solution, okay? And it is asymmetric, and at the minimum, it's a positive semi-definite matrix. Its eigenvalues basically tell you about the curvatures along different directions defined by the eigenvectors. Okay. And for this specific example, in which we have this learned solution for the very simple task in which we have a fixed input-output relation, we find that, this is just an example, we find that the spectrum, the eigenvalues of this cost Hessian is highly degenerate. Now, that means that most of the eigenvalues are concentrated around 0, meaning that in almost every single direction in parameter space, the landscape looks flat, except for one direction in which the curvature is huge, all right? Meaning if you take one step in this parameter direction, you climb up the cost and you basically lose the learn solution, the learn function. Now, this property of having this highly degenerate spectrum is not due to the physics of the problem, but mainly due to the fact that we are optimizing an over-parameterized problem. And you also find this in deep learning situations. So what is the stiff direction? Okay, so you can guess what the stiff direction looks like. It's basically highlighting the crack of very low conductance. Because if you were to perturb any of these conductances, you're basically short-circuiting the network. And you're basically, you cannot hold this difference of voltages. All right. So the cost Hessian relates to the learn function. That's the meaning. It tells you that, for example, the large entries of this stiff eigenvector are my key components for whatever function I learn. If I perturb any of these black ones, I basically climb up the cost and lose my function. And so since we have this double optimization problem, turns out that the cost Hessian depends on the physical Hessian. It does not surprise. This is one of the things that we observed in one of the papers. Here again, just for simplicity, for fixed input-output relations, we observed that the stiff cost eigenvector, that's in cost space, is basically the softest mode in physical space. Now, the stiff eigenvector lives on the edge parameters. The soft mode lives on the node parameters. But if you were to take the voltage drop, okay, here everything is 0, here everything is 0, and the only non-zero elements are the ones along this crack. That's the first observation. The second observation is that you can compute the cost eigenvalues, you can compute the physical eigenvalues, and you find a relation between the stiffest and the softest one for many, many networks. This is more than 1,000 networks. And this was a first suggestion that within these physical systems, it is possible to know something about the learned solution only from physical information. And I want to highlight once again that in order to define this cost Hessian, you need to know the cost. You need to know the task that you were training for. In order to know the physical Hessian, you don't need that. This is just a physical property. You hand me a network that was trained for something, and I can compute directly the Hessian and the soft modes. And so there is this notion of maybe we can infer things about the learned solution only from physics. But as soon as we go to more complicated tasks, that is not only the fixed input-output relation, but tasks in which we have to generalize, all right, we get into trouble. And here I'm showing you two examples. One example is to train for regression. It's not very complicated, but still more complicated than the previous one. For example, here I have in blue my output nodes, and what I want to learn for this network is a linear relation as a function of my inputs, which are in red. Or you can do the same. Here I have two input values, and I want to classify this into these three classes marked by these three output nodes. Turns out that this relation that we found for the very simple fixed input output relations do not hold anymore. So we had to dig a little bit deeper. And we had to know, okay, what's the actual dependence of the cost Hessian in terms of the physical Hessian? Okay, so this is like the most mathematical slide, I guess. And so we define the cost. And we define the cost as a sum of constraints. So here the R index is going to be an index over all your samples in your test dataset, for example. The constraint is basically going to be the difference between output and desired output. Here I write it down in terms of the inverse of the physical Hessian. I want to compute the cost Hessian at a minimum. And just for simplicity, I'm going to assume for this case that I'm at the minimum, the cost is actually 0. You don't need this in practice, but the math is simpler in this case. You can compute the Hessian, and in this case, it's going to be the sum over all the test samples of the outer product of the gradient of the constraint. And the gradient of the constraint, if you compute the derivative here, it's only basically taking the derivative of the inverse of the physical Hessian. You can rearrange all the terms, and at the end of the day, the cost Hessian can be written as the contraction of 2 tensors, 4th order contraction. One tensor that contains all the training information, that contains the sum over all your the test data or training data over the output nodes and input nodes, and something that's purely physical, okay, that only contains the information about the inverse of the physical Hessian. And so we have this is decomposition. This is only training, this is only physics. And by the way, we call it susceptibility because we know that the inverse defines the response, and this is basically saying how the response changes when we change the parameters. So all the physical information of the cost Hessian lies in this susceptibility tensor S. So what is this object S? So last line of math, we compute this derivative. Okay, this is just by definition the derivative of the inverse. And now we only have to derive the physical Hessian. Remember the definition of the physical Hessian? Okay, this is linear on K, so you compute the derivative, and what you have is this object here. We define this quantity as what we call the susceptibility vector, and at the end of the day, what we have is that the susceptibility tensor is the outer product of the same vector 4 times. Okay. So first thing to notice, the inverse Hessian appears 4 times, which is in agreement with what you observe numerically, that the cost eigenvalue of the stiffest eigenvalue of the cost Hessian scales to the power -4 with the softest of the physical Hessian. The second part is that Si is a vector defined per edge I, and each entry has a physical meaning. In fact, Si alpha is the voltage drop at edge I due to unit current at node alpha. Here as an example, I'm plotting the susceptibility of this green edge here. The susceptibility is the background color. You can see that when you go far away from this green edge, the susceptibility is very low in magnitude, and as you go closer and closer, it starts to increase. So the susceptibility is 1 vector per edge. You can take the norm of the susceptibility and somehow compute the total susceptibility per edge, and what you have is this scalar field. And this susceptibility reflects the network structure. It's basically weighting in the conductance values through the inverse of the physical Hessian, but also the connectivity through the incidence matrix. And what we have at the end of the day is that the physical constraint, the fact that we have to minimize power, leads to structure function relations. At the cost Hessian level, we see that the cost Hessian can be decomposed into something that's purely training information and purely physical information. But you can go 1 level down. You can even write this down at the level of the eigenvectors. So I'm not going to derive all the math, but you can write down the stiff eigenvectors of the cost Hessian in terms of the susceptibility. Once again, you can see how physics appears here into the cost eigenvector. And here A is a matrix that depends basically on L, once again. And we have this suggestion from this expression that it seems that highly susceptible edges may lead to high entries, to large entries of the stiff mobs. And the large entries of the stiff mobs were the key components of the learn function in my network. And so for this very simple example of linear regression, we can just analyze in full detail, for example. For the cost landscape, this is the spectrum before training. The spectrum before training is just a mess. But after training, it gets degenerate. It focuses around 0, and you have, in this case, 4 stiff eigenvectors, which relates to the 4 linear components that you have to learn. These are the eigenvectors. And this is what you obtain from the cost landscape. From the physical landscape, you can compute the susceptibility. And you can see visually already that the physical, that susceptibility already defines what the stiff eigenvectors can tell you. And in fact, if you compare numerically, you can see that large susceptibility leads to large entries of your stiff eigenvector. And yeah, well, and this is quite generic. You can repeat it for many, many problems, classification and regression. And again, we have this structure function relation that's only due to the physical nature of our systems. Beyond the structure of these train networks, you can do even more. You can now look at what is the conductance of these highly susceptible edges. And we find in general, these highly susceptible edges tend to block current. Okay. We also find that the susceptibility of train network is dominated by physical soft modes, which is in line to previous articles of Nahi and Andrea. That for other kind of problems, these fixed input-output relations, this susceptibility recovers the functional sectors of allosteric networks, which are relevant for proteins. And in general, that physical constraints lead to structure function relations that might potentially lead to interpretable solutions. And so I think I'm going to conclude by here. But basically what I told you today is that this constraint of Kirchhoff's law, which in linear systems reduces to power minimization, can give us insight about the learned solutions that we find. That this stiff eigenvector in the error space basically corresponds to this susceptibility that we find from the physical space. But this is only one type of physical constraint. In fact, there are many other physical constraints. When you look at this real system, one of the actual physical and practical constraint that we have is that these systems are imperfect. They are messy. You try to make two edges identical, and they are not. And that has consequences into the learning dynamics. Okay, so I put this here if you want to discuss afterwards, but what we observe is that because they are imperfect, we observe things like representational drift, like in the brain. We observe that we have a lower performance, but we can also improve it by changing the boundary conditions of our learning algorithm. And lastly, when we add noise and nonlinearities, and in addition, we have this constraint of minimizing power or Kirchhoff's law, we can actually build learning circuits for unsupervised tasks. And this is in link with the restricted Boltzmann machine. So finally, let me just thank my collaborators that did a lot of this first work, these first two papers, funding sources, and let me take any questions you may have.
If I understand correctly, what you discussed is about linear, so the input-output relationship is always linear.
Yeah.
So you can do a linear classification. But if you want to go further, you need to have non-linear classification.
Yes.
But then you would not have a single physical relation. I mean, depending on the input you look at,
Yes.
you will have a plethora, or you will have a big number of connections. So what would then be the connection between your loss station and the physical one? So average?
Yeah, that's a good question. Yeah, so everything I said was about linear regime in resistor networks, satisfying Ohm's law. You can then start playing the game. What happens if I have 2 minima, for example, or 3 minima in my physical landscape? Then, of course, the information of this minima may be irrelevant for the input-output relation when you apply the inputs. And there, what you have is that for every single minima in your physical landscape, you have a different connection, you have a different susceptibility for the related to the minimum of the cost landscape. So that's the first thing. We are currently exploring this venue with simulations because having the analytical simplicity of a linear system is not longer available. And we find that that's indeed the case. Okay. Other thing I want to mention is that even though the system is linear, you can attempt to solve complicated tasks. You can attempt to solve nonlinear tasks, nonlinear regression or nonlinear classification. The network, of course, is not going to perform very well, but you can still be at the minimum of a cost. In that case, you can still have the same kind of relation, meaning large susceptibility implies large entries of the stiff vector for the best outcome that you could have expected from this network. Yeah.
Thank you for the great talk. I have a question, kind of like, I'm not even sure if it's mostly addressed to you or to the previous speaker, but this problem that you mentioned, that essentially like the networks that you're building are imperfect, right? And coming back to the design with these sequence networks that the previous speaker demonstrated, isn't it a problem that essentially the two networks, they're not identical? And that's why when you compare the difference between them, there would be some couples, right? So,
Yeah, that's actually what happens in practice. Yeah. So we in theory we try to implement the couple learning rule, okay, and we assuming that everything is perfect. But what the inner circuit updating the twin edges does is to try to implement that, but there is some noise, there is some bias, there is some drift. And what you get in practice is that instead of moving in a predictable way in parameter space, you are deviating from it. Okay. And what we do here is that first we quantify these deviations, we explain it through a bias term, but in addition, we try to render the learning algorithm more robust to these unforeseen imperfections. And one way of people doing, so this is very interesting. So a lot of people doing learning in physical systems have to have to error correct for physical imperfections. Here, we don't want to measure how imperfect our system is. We know they are imperfect. We know that it's going to be a pain to describe the imperfections. So let's find rather a learning algorithm in which you can be robust to all these learning imperfections. And that's what we do in this paper, in which we change the nature of the boundary conditions. We change the time, how long we keep the boundary conditions. And just by playing with that, and with the strength of the boundary conditions, we can basically overcome these imperfections and we can learn better. I'm happy to talk more about it after the talk, but this is
like even like the boundary conditions, they're also imperfect, right? So
yes, everything is imperfect. Yes, everything is imperfect.
You can kind of like trying to minimize the impact of those imperfections, but it's the boundary conditions themselves that
Yeah.
are imperfect, and for that reason that's going to be propagated.
Yeah, I totally agree with that. I mean, we cannot get rid of imperfection. We can try to mitigate them, but imperfections are going to be there. Like in biological systems. I mean, biological systems are very messy.
Maybe I can mention that from protein aerospace model, you also have self-mod emergent, and then it's true that if you get the tension of the loss, you do find that sort of connection where both the loss are large strength.
Yeah.
Actually, I think there is evidence of that.
Yeah.
In real world.
Yeah. Actually, yes.
So mutation affect more where
Yes. Yeah, we're very excited about this. Everything I told you was about resistor networks, but the same thing applies to mechanical networks. It's the same math, except that instead of voltages, you have displacements. Instead of conductances, you have a stiffness. And then you can apply the same way to systems in which, for example, you do not know what it was trained for, like biological systems. But here we have this physical window in which we can actually analyze, in which without having 100% certainty of what the network is supposed to do, we can try to understand what the most important components are. We can maybe infer some useful information about them. I don't know if I have.
There's a postdoc Rashid Mohammed Rafiq, who is looking at this, and the idea is that we can pull out the key amino acids without needing the mutational skills that really are important for function. Just from the physical health.
We looked at that because of our library, but that's the network description of protein that we saw from it.
All right, let's thank Marcelo. Have lots of questions. That's
Okay. Mike Weiner. Um, Are you on there?
Yeah, I'm on.
Share the screen.
Great.
Pretty good job staying on.
Right. Thanks for the invitation and the opportunity to tell you about our work. So it's going to be rather general talk, but I will focus on very specific results within the last few years. And when I mentioned computing with physical systems, this is really in the spirit of the previous two speakers, Andrea and Marcelo. But today's my talk today is going to focus on the low energy regime and fundamental limits. So what do I mean by this? Imagine the previous resistor network situation and look at input voltages where the encoding, the input voltages, physical quantity, is reduced to lower and lower amplitudes, you know, at a level that it's almost maybe one photon, right, at that energy. So can I still do the computation? And what are the fundamental limits? And you know, hopefully the point I'm gonna be making that will come across is that this is really best investigated within quantum theory. So that needs to be the starting point. So I'm gonna be in this talk again. When I say computing with physical systems, I'll be interested in data-driven inference or machine learning in modern jargon. And I'm going to be talking about this notion of physical neural networks. And I want to be very concrete about what I mean by physical neural networks. So deep neural networks, now pervasive tool in science and engineering, you can think of this as a mathematical transformation that takes an input, U, and transforms it into an output. I'm going to call these features, and these outputs are functions of that input. So I'm always going to use this notation where U is a vector, you know, large sometimes, and represents the input. And these XUs are going to be the nonlinear output features of the system. So I just put in a U, I get an X that is a function of U, and that's going to be a function of these input parameters. But for this talk, I'm gonna assume that this theta is something you optimized already. So we are going to be talking about the inference stage within supervised learning framework. Yeah. So now the physical version of this, you know, I have an example here. This is not something I'm going to talk about, but I feel it's more, you know, human-friendly optical situation. There we are going to be thinking about this mathematical transformation that gives this output features be implemented by simply the evolution of a physical system. And for that, you can imagine like the input now, this is an optical situation, the input being on the spatial light modulator, you know, a digit that you want to maybe classify, light passing through this. This is my physical system parameterized by these parameters theta and mapping it onto some pixels in this EMCCD camera. So then you want, you know, this essentially, when I look at individual pixel values, I'm going to be talking about nonlinear features. That is a nonlinear function of the input U here. But I want to point out first the difference before mentioning what is our goal of my talk today. I want to understand the function space that is spanned by these nonlinear features for a given input set of parameters. And what is that function space? How do I think of this? And that means I'm gonna take these features and I'm looking at the function space that can be spanned with these weight vector, with this weight vector WO. Yeah. How big is this function space? What functions can I represent? Now, let me come to the important difference between a deep neural network and a physical neural network. Here, the inputs can come from the physical domain. I mean, instead of storing digital images in memory in a digital computer, this can come from the physical environment that input information. And the transformation is a physical transformation and includes a natural physical transformation between physical stimuli. I mean, from optical, you turn into electronic excitation, right? And all this is constrained by laws of physics, right? And when I try to extract the output features for a given input U, then I have to do that through a measurement. And so this is where we need to be very precise, because these features, they invariably are extracted from some averaging procedure, right? If it's pixels, and in particular, when the energy here, the light illumination is very, very low, maybe a single photon is seen per sort of detection, then the features are really stochastic features, right? And again, this is why I represent this with a capital X and a bar, because in such a situation, it could be an integration over delta t, and these x's could be how many blips do I see here for a given input U. This gives me a vector x. And then the question of what is the function space I can represent is actually recedes to the background, because the important question is what functions can I resolve, right? Now, and that's a very different question, it turns out. And that is one that one can really quantitatively describe with a mathematical formalism and the laws of physics. And that's I made a choice, instead of telling you about different projects that we have been busy with in the last few years. I'm gonna just hopefully share this particular result about how do we quantify the space of functions that a physical system with given internal parameters can represent. So now, when you come to this very low energy regime, and this is a result that is in a paper, but it's very hard to extract. Yes?
Are you interested in the function space or
Distribution. I'm interested in the function space, but there's going to be a distribution, a stochasticity due to repetition, which I will describe now to be concrete. What distribution, what stochasticity I'm talking about.
I guess I was asking probably
exactly, and I want to know what those functions are given a physical system, and how do I characterize how many functions my physical system can resolve. Yeah. So this. So it turns out that when I ask about this very low energy regime of encoding, right, I input my information into my system at very, very low energies, then it turns out to sort of have the capacity of still very high expressive capacity of my physical system. You can show that I have to crank up the nonlinearity in a certain proportion. Yeah. And that automatically takes you to the quantum regime of single quantum systems, And I want to discuss how that happens, how to think about that. Yeah. So here, and I want to discuss that within the context of a toy supervised classification problem that I'm sure you have all come across, which is the spiral classification task, and how one way of doing that with a quantum computer, like a quantum processor, superconducting quantum computer, gate-based, doesn't need to be analog. And how do you do that? Well, here the task is someone draws a point here. It comes either from one spiral arm or to another spiral arm. Each point is represented by a two-dimensional compact variable space. You take this U1, U2, you encode the evolution of this 4-qubit system, let's say, where we start each time with all qubits in the ground state, right? And then you evolve for a given U this system according to this prescription, and you get outputs. Outputs are projected measurements. You get bit strings 1, 0, 0, right? 0, 1, 0, 0, and there's a stochastic distribution like this that you get. From those, you build up a measured feature space. And now I'm asking, what functions can I access of my input U by playing with these weights, WO? Yeah. And you can think of this as a decoder of my information. And so, there are many ways to sort of extract from measurements, build up these measured features. One way is you could, for each U, you measure the expectation value of Z, and you make a vector of these. And then you do it for a different U, and you try to train your system to execute a function you want. In this case, the function you want to implement by finding the best W here is one where if I give an input U1, U2 from here, right, and I measure and get this output, I want that this F is 0 for the blue points, and it's 1 for the green points. Yeah, that's my toy classification problem. Yes.
So you're not fiddling with H of U, it's like measurement-based quantification and then that.
I know it's because it's for us a separate problem. Yeah. This to me is how I think of the function space, that I can deal with nonlinear features coming from this sampled physical system for given inputs. Now, the cost function I'm gonna minimize, right, to make this system do what I want to realize this function is 1 minus the loss, the typical square loss. Yeah, and there's a reason I use 1 minus. I will call this capacity to represent this function f star, where f star, my ground truth is this, right? And this is just 1 minus this. And the way I actually normalize this f is such that this number c is between 0 and 1. It's a compact variable. If it's 1, my f that I build from fiddling with this w is exactly f star that I want. So then c is 1, and it can at least be 0. Yeah, so it's between 0 and 1. So once you maximize this, find the w that maximizes this, and you can then scan the u's and see what kind of function that perfect w gives you. And it is this form, right? In blue regions, it's 0. In these green regions, I'm colorblind, so I'm probably confusing colors, but you can probably distinguish this, which I can as well. And the separation boundaries are at 0.5, where that function takes a value of 0.5. Yeah, this is done actually for a 4-qubit system. Yeah, and now you can test it by giving points from these spiral arms. These are the test points, and see what the sort of accuracy is. It's 94%. Yeah. So this is the kind of how I think of functions that I can span with this quantum system.
Sorry, doesn't this really depend on how H depends on U?
Yeah. If you choose a different parameterization of
But it might be possible that you choose such an age that no matter what projector, you cannot make a projector that basically will distinguish.
You can still come, will have an error, right? And that error will be stochastic, due to the, we'll talk about it. That error will partly be due to how well this physical system can encode this, to by sampling noise, which I didn't talk about yet. Okay, so this is how I think of a quantum system, which is projectively measured as a function generator or approximator. Yeah. Now I want to formalize things. I want to say, well, how do I, this question of how do I really characterize the space of functions that that my physical system can access by just within this function space of nonlinear features? Well, what I'm going to do then is I will come up with a complete set of functions FL star, right, that live in the input domain, calculate the capacity for each FL star, sum them up over infinite set of orthonormal functions, and get this, what I call the total capacity, right? And then you can ask what is this total capacity of a given physical system? And turns out there's a neat, very nice mathematical result that actually inspired much of our work from 2012, that this total capacity is really bounded by L, where L is the number of linearly independent output features that this physical system can generate. And this is an equality if your physical system doesn't have a particular symmetry, hidden or explicit. Yeah. So this is an equality. This is what it's bounded by. It's a very powerful result. Now, of course, from this point of view, all physical systems with L independent degrees of L measurable independent degrees of freedom are equivalent, unless they are symmetric and so on. It's not very helpful because in physical, when you really do you actually spend some time in designing your physical system to get a better capacity. And so where is the sort of the gap between reality and this physical result? Well, that turns out to be in the noise. Yeah. Because if I apply the same ideas to my quantum system, for instance, right, like the way I described, I have my input space, I take 4 values here, and I calculate the expectation value of, let's say it's 2-qubit system with a very simple, input encoding. You see, it's very simple. The input is encoded in these RX gates, and then I measure individual qubits. I can calculate expectation value of Z1 and Z2 for each input U, and these are those points, and I can plot this also in the 2-dimensional domain. So it's a map from a compact space to a compact space. So it's very nice. I can play with it. So again, just to visualize. But in reality, to extract these expectation values, I need to actually make a finite number of experiments. Yeah, and let's say usually you talk about that in terms of a budget of number of shots, number of experiments, number of shots. So then for each S-shot experiment, I actually get a value that fluctuates. This is for this particular in U, right? And I'm showing the result of S-shot experiment in terms of what for this U, I get in this Z1, Z2, it fluctuates. Now, as I increase the number of shots, that distribution gets narrower and narrower. This green is 10 power 4 shots. And so there's this sampling noise error there, which is most explicit in these kinds of quantum systems that are projectively measured. And only in the infinite shot limit does this reduce each of these distributions reduce to a point, which is the initial assumption here, right? And then from naturally, if you represent now any function from these guys, then it will have a natural error that is due to the fact that in an S-shot experiment, you will get one value for this F, but for a given U, but for another S-shot experiment, you will get another value, and you need to understand that width. Now, the big observation here is that, okay, first of all, this indeed is what happens in experiments, and these experimental systems really produce the kind of distributions that are very close to what we would numerically get. You know, this is a numerical random number generator doing this for the circuit. Yeah. All right. So so that means now I'm going to talk about like a way of doing machine learning with quantum systems that is informed by this noise. The fact and what you observe here is for each U, these distributions have a very different structure. Yeah? Some are very elongated, right? Some are more Gaussian-like, and so on. And turns out that their structure, that noise, is again dictated by quantum mechanics, but not by random noise. Yeah. And so I'm going to tell you about some algorithm that we have developed and are using that essentially makes use of this structure in the noise to extract information beyond just the average values. Yeah. So now let me come back to this thing and to this total capacity question. Right now, it is more nuanced. Now I have to ask this, for a given S-shot experiment, what is this total capacity? And this is just an illustration, right, for Legendre functions, for input that is drawn from one-dimensional input, Legendre function number 1, 2, 3, 4. For an infinite shot quantum system, the fit is almost perfect up to large values. But then when I have noise, then these are the results for an S-shot experiment. So the total capacity will never sum up to the total thing given by L, but less. So now the question is, what is this less? Can we quantify this, how much less it is? So here, okay, I have to speed up now. This quantum algorithm we call NISQ-RC, and the way it works is for every input U, you parameterize this evolution with the same input, you get an output. And the output is, as you know, for an S-shot experiment, is this histogram. How many times what's the frequency of observation of the outcome 0, 0, 0, 0, 0, right? And you have 2 to the power L such outcomes. It's a categorical distribution with 2 to the power L outcomes. And that's the quantum part of it, that this is exponentially large in number of qubits. And then each of these heights, frequencies, I return into a vector. That's the algorithm. And we try to find this, optimize this W to give you a function that you want. And yeah, but it can be straightforward generalized to non-unitary as well. The limits will change, but yeah. So this is the one slide summary of this question of what is the total capacity of a L qubit system. Now, in the case of a projectively measured L qubit system, the total capacity can be computed and tightly bounded. And this total capacity, right? This is the capacity of how many orthogonal functions can my physical system get? And it can be written in this form: 1 over 1 plus 1, 1 over 1 plus beta k squared over S. S is the number of shots per experiment, per view, the input. And so it's a number, it's a sum over these terms. And the number of terms is 2 to the power L, where L is the number of qubits. So first of all, you see that when S is infinity, this is a sum over ones. And the result is 2 to the power L. So which means for an L qubit system, the total capacity for infinite shots is just 2 to the power L. But for finite shots, it's reduced according to this formula. This is where S shows up, the only place where S shows up. These are numbers that are independent of S. how many number of experiments you do, and are obtained as an eigenvalues of a generalized eigenvalue problem, and where the matrices can be set up from experiments. You do experiments for every U, you get the measured feature vectors, and you construct these matrices, which we call the Gram matrix and the covariance matrix, and you find this beta k square, and you sum them up. It gives you how much total capacity is reduced from the infinite shot limit, and this is really the practical, very practical result. This result is in this 2023 paper here. Now, I want to draw your attention not only to these eigenvalues, which we call the noise to signal ratio eigenvalues, but also to the eigenvectors. These eigenvectors, which you can construct from experiments, estimate from experiments, they turn out to be the particular combinations of features of X's that gives you the highest signal to noise ratio functions that a physical system can generate. And so these R's are, each of them is a set of coefficients, set of ways you linearly combine these features with X's with to find functions. And those functions are high signal to noise ratio. And I will refer to them as eigentasks corresponding to these eigenvalues beta k square. Instead of getting into mathematical detail, I just want to show you how this thing works out in experiments. Yeah, concretely. How much time do I have? Really? All right. I mean, yeah, that's a discussion, so we can carry this out for another hour. So I'll probably just present this result, and we can discuss offline if you're interested about other results that build on this. So here, this is we did this experiment on actual quantum processor called Perth. We use 6 of the 7 qubits, and so the 6-qubit system. And there's certain encoding of the input, and this is you see U is hidden here, the input is here in the Z rotations. But the only thing you should remember is it has some internal parameters which we leave fixed. This thing, J, tells you about 2-qubit gates. If J is 0, then there are no 2-qubit gates, and this is simply a product state encoding, product state generated by your encoding. So just remember that. So for a given, so we will draw the inputs from one-dimensional uniform distribution U minus 1 to 1. And for each in this domain of U, now if you look at individual features, the occurrence of the bit string 0000 in S shots, it turns out it's this. This is the measured result. Yeah. So it's an interesting function. Yeah. It's just the frequency, how it varies over the inputs U. And now this blue is the experimental S16384 shot result. And the other colors are numerical experiments with the given error model and without error model. And both are very close. The one with error model, correct error model at that time of that chip has an even better correspondence. So these machines really operate at a limit where these functions are well defined. Yeah. And now I'm plotting here the eigentasks, which are 64 in number, right? 2 to the power 6, because you have 6 qubits, every fourth of them as a function of input U minus 1 to 1. And there are two, for each eigentask, there are 2 plots. One is 16,384, the dark blue, and the other is 1,024, which is this lighter blue. And you see that the lighter blue thing is a little noisier version of the dark blue version, right? But the general trend is as you go to higher eigentasks, high beta k squares, the corresponding eigentasks get noisier and noisier, as I promised. And beta k squared turns out to be the 1 over signal to noise ratio in approximating this particular infinite shot version of that function. Yeah. So if you're interested in how these beta k-squares are distributed for two different input encodings, they are shown in blue and this color. And you know, this is the order, and there are 64 of them, and they are distributed in a very interesting way. There's a universal distribution we observe. There's a super exponential increase. This is a what's called logarithmic sort of scale here, right? And the important sort of rule of thumb that you can adopt is if this beta k-square is very small, then this is almost 1. For those eigenpaths for beta k-square is very large, it's 0 almost. And the boundary between them is given by S, the number of shots you use in an experiment. So I can, in the beta k-square space, I can draw this line of S, let's say, you know, 2 to the power 13 shots. And what this tells you is that total capacity is really sum over all the eigenvalues below this, number of eigenvalues below this line, and it gives you total capacity. In fact, when we plot the total capacity for number of shots as a function of number of shots here, utilizing these, this is how it increases. There's in this logarithmic plot of shots, the capacity increases in this fashion, in a monotonic fashion, for two different encodings. And you see, for a given number of shots, the blue gives you a better performance. It's different internal parameters, different encoding. Why? Well, it turns out the green is the one where we keep a encoding circuit that doesn't have entanglement. It's only product states. There's no 2-qubit gates. And the blue, which gives superior performance, uses some amount of correlations. Yeah. And so that was very interesting to us. By the way, 64 is the total capacity. So these guys are expected to go up and saturate at the 64. We are not there yet. So these machines are limited by shots, not by errors, like circuit errors. I will close with this very interesting observation. So because I told you that there are these two encodings that gives you different sort of eigenpaths, different total capacities, we were interested. So what in encoding maximizes this total capacity of a given circuit? And so here is one very simple way of looking at this problem. We are changing the coupling J. The coupling J is the strength of 2-qubit couplings, or in other words, 2 spin interactions. And you see, as a function of J, capacity increases, reaches a peak, decreases, and has a particular structure. And the point, so you're naturally interested in the point at which total capacity is maximized. Where does this happen? Coupling pi over 2 in a certain sort of encoding and parameterization of the system. Turns out this value of 2-qubit 2-spin interaction at which you get maximum encoding is close to around the critical point of this encoding. So encoding is the trotterized, we chose it specifically to be a trotterization of transverse spin Ising model with random parameters. Yeah. And U, the input, is entered as one of the magnetic fields. And so at the point where the total capacity is maximized, the system is close to criticality. Yeah. So it's not surprise because the system near criticality has a high susceptibility to input noise. It's two inputs, which we want, right? We want a good response to U that we put in. So that gives me more functions and more resolution. And so I think one open question that we really would like to answer this is how general is this observation? Can one analytically somehow show that you actually want to operate these physical systems near criticality, some kind of criticality? And this turns out in some other work is related to actually soft modes, yeah, of these physical systems. So, you know, it's very interesting discussion, and I will skip these. It can be applied to optics and so on, and you can do this in time domain and so on. And let me come just the people who worked on this and who are the main contributors, Said Khan, Fengjun Hu, and Jerry Angilados, all of whom have left the group by now. Marty is continuing still, Essen from Physical Computer Science, Graham Rollins and Guillaume Rubé from Raytheon DBM, now RTX, and Nick Brown from IBM Quantum. And I want to also acknowledge the bigger Muri collaboration and my co-PIs in this collaboration that were part of this work. Thank you.
Unless there's actually next speaker probably line up while we're switching over. If there's a quick question. I don't.
Yes. Yes. Generalization.
You're asking about memory capacity of a computer network.
Not memory.
Because they're
This function approximation capacity. So that is slightly different. It's a different way of thinking is what I want to say. But it's similar. Same. I mean, we are understanding finite limits to that capacity given finite energy that you put into the physical system and finite resources like measurement resources and so on.
right.
Yeah.
And there's this additional fundamental.
And additionally,
But in some sense, they're also like the memory capacity, something which, you know, models, depending on what Hamilton will take.
very much. Yes. So there's a scaling of the number of memories you can store, right, in that context. But that's again, so here the question is, what functions can I approximate with my, as a function of my inputs? Functions of my inputs can I represent as a physical system? That's a different question. And so, of course, it's also bound. But you ask a different question, which is more relevant in the context of supervised machine learning and things like that. And techniques can be similar, of course, mathematical techniques.
That works.
But,
Yeah, I don't know what you're doing.
Yeah, well, one last question.
One question.
We're struggling with passwords.
So in neural networks, you know, people just worry about input noise. That's the only kind of noise that they're worried about.
Yeah.
But in physical neural networks, there are all different kinds of other forms of noise.
Yeah.
When you say you were talking about mainly output measurement
yes,
noise?
yes.
Okay.
Output noise.
Yeah, but there's also weight noise, right? The weights, the way there's noise and.
Of course, yes.
But the weights.
By,
are-
by that, so we have to be very careful about what we do and identify noise.
Yes,
I'm very specific about what we
yes.
do.
And it's output measurement.
You guys are wrapping up.
So it's not time dependent, so we do not consider time dependent variation and random variation. We are only looking at, let's say I fix W and my physical system upon repetition has same
Always
weights
the
and so
same.
on, yes. But still, there's the output stochasticity, and that's because of fundamental Schaffhouse. It's quantum.
Okay, we have one more talk in this morning session. Thanks a lot. Oh, I'm sorry, did we thank Hakan? I'm only taking extra 10 minutes. Okay. Mike,
luckily some physicists are
I have to say that the intention was to make the morning session about physical computing, but then I remembered John Torilla, who was one of the co-organizers, was going to be here in the morning, and I think he was looking forward to hearing Mike, so I did some
Okay.
surgery.
Okay, yeah, well, this is not physical computing at all.
Right, we might have to, activate another part of our brain.
Okay.
Go ahead. Thanks.
So yeah, my name is Mike Weiner. I work at the Institute for Advanced Study, and over the past few months, I've also been working with a research group called the Alignment Research Center. We were studying heuristic estimations for multi-layer perceptrons. So this is like sort of given the weights of an MLP, or hopefully one day something more complicated, what can we analytically say about the behavior of this particular neural net?
Sorry about
Okay, so
Actually, do you want to put the computer there? You don't mind?
probably is a little wiser, yes.
Yeah, well, the
Um,
microphone also is close.
Okay. So yeah, let's, the plan is, first, I'm just gonna, describe the problem that we solved. And I'm gonna talk about why this problem is worth solving. So the problem that we solved is given a particular neural net, in this case, a one hidden layer MLP, what can we say about the distribution of outputs analytically? Why did we solve this problem? We think it'll help, among other things, with more robust methods of training, as well as just being in some ways like the soul of interpretability. How did we solve this problem? We figured out how to calculate the moments of the output and relate them to various tensor network contractions. And then we spent a huge amount of time going through tensor network literature, trying to understand how to do those efficiently. And then I'm just going to talk a whole lot about all the problems I'm going to have to solve in the future if I want this to actually be useful. More complicated training regimes, more complicated architectures, more complicated inputs, more complicated everything. Okay, so a little more detail on what we did. The goal is one hidden layer MLPs. We want the average of the final activation. The simplest algorithm you could come up with to figure this out is just throw in a bunch of inputs and take the average. And this is, a reasonably effective method, assuming there's not wild variation in the output. If you want error epsilon, this is going to take 1 over epsilon squared forward passes. But we do find something which is more efficient. Depending on the exact setup, it's either much more efficient or super duper more efficient. Furthermore, our results are mechanistic. They tell you like what aspects of the neural network, not like these weights, because like that's not how things work, but like these correlations among the weights are what's responsible for this particular behavior. So some details on the setting. We can use completely generic activation functions, ReLU, tanh, whatever you want. We solve this with neural tangent kernel parameter scaling, although with a little bit of elbow grease, you can do other scalings. And we solved it for whatever hidden layer width you want. Although in this talk, I'm going to mostly talk about where it's ridiculously wide. So here's a picture of a multi-layer perceptron. As you can see, 6 is much, much bigger than any power of 3, which is why we can approximate the hidden layer weight as being way, way bigger than any power of the input layer. Yeah, so the input layer, we give it width n0. We have all these weights, which scale as 1 over square root n0, keeps the pre-activation O of 1. Hidden layer weight is n1, which again is ridiculously big. That's why it's 6. Then these weights scale as 1 over root n1 in order to give you another nice pre-activation for your final output. You can use whatever activation functions you want. We're calling them G and F. Don't have to be the same. They can be whatever. So yeah, why does this matter? Well, we care what behaviors show up in our AIs, right? Right now, the only behaviors we're looking at is when is the output equal to 2.7. But with higher dimensional outputs, of course, you want to know what the behaviors are. And a lot of the time, we care about very rare but extremely undesirable behaviors. You can think of jailbreaks. You can think of when the AI gives harmful advice. I'm sure thoughtful people like you can think of all sorts of other examples of events that are so bad you don't want them happening even 1 in a million times. But if you want to find things that happen 1 in a million times, at least naively, you need 1 million forward passes on different inputs. And this allows you more efficient ways of finding how often these bad events happen. You can gradient descent not on these particular bad inputs, but on this estimate of how often bad things happen in order to hopefully more efficiently remove bad behavior. So that's a sort of practical reason why some descent into this work will be quite useful. But there's also, I think, a more philosophical reason, which is just this is interpretability, right? This is looking at the weights and saying, here's what the network does, which is just, to me, valuable for its own sake and also has a huge number of other important applications. And I think this will be a lot more robust to distribution shifts, right? Like in many, many ways, especially jailbreak related ways, but all sorts of other ways, the test time distribution will be very different than the training distribution. And the methods we're coming up with should be more robust to that. Okay, so that's what we did and why we did it. Let's talk about some math. So I'm mostly going to be talking about untrained MLPs, but we went beyond that. The important thing about an untrained multi-layer perceptron is that the input to the last layer is almost Gaussian. In those of you who think in terms of cumulants, the first two cumulants are non-zero and all the others are suppressed by factors of ends up being the input width. So if we can calculate those cumulants, we can sort of set up the equivalent of a perturbation expansion. Statisticians call this sort of thing an Edgeworth expansion, but hopefully we don't have any of those in the room. The strategy, we're going to get the moments of the final preactivation, and then that gives us the cumulants, and that gives us the distribution of that final preactivation. Then you can just go forward and take the average and win. So how do we get these moments of Z2, Z stands for preactivation 2 because it's the second layer. How do we get the moments of Z2? Well, this final preactivation is just this weighted sum of all the hidden layer things. Each of those hidden layer things is a simple known function of a Gaussian variable with some principally knowable covariance matrix you can extract from the weights. The issue is if you do this the naive way, if you want the kth moment, you need to sum over like all n choose k sets of hidden layer neurons. And because we are interested in the case where n1 is way, way larger than everything, n1 to the power of k is just prohibitively expensive. So a lot of the cleverness and effort here goes into just finding a more efficient algorithm to do this sum, rather than literally going naively through every single k tuple of hidden layer neurons. So this is Norbert Wiener. He invented a concept called Wiener chaos. This was before physicists developed the concept of chaos theory. So he actually has first dibs on the word chaos. His idea was basically what we would now call expanding a function, well, almost a Taylor series. I don't know why he called it chaos. So given some variable z, which in this case is going to be that final preactivation, represent it as a sum of polynomials, in this case, Hermite polynomials, which are some special, beautiful basis of some nice Gaussian variables. So in this case, yeah, we're going to represent our that final preactivation, which is itself almost Gaussian, as a sum of Hermite polynomials of the inputs. Okay, and I have some somewhat scary looking equation. We ran out of English letters, then we ran out of Greek letters. So someone suggested the Hebrew alphabet. This is going to be my greatest scientific contribution, is discovering a new alphabet for when your equations run long. An upcoming paper will use the Cyrillic. Yeah, we call this the Shin tensor, and it just the dth Shin tensor is an n1 to n0 to the d size tensor that encodes all the coefficients of your Hermite polynomials. And so why is this a useful rewriting? Well, each Shin tensor is fairly simple to calculate. Each entry, you just need to sum over all the hidden layer neurons. So the cost of a given Shin tensor is n1 times the size of the Shin tensor. Remember, the cost of a single forward pass is roughly n1, n0. So it's like less than a forward pass per entry of the Shin tensor. To me, they are fairly interpretable, right? It's expressing this thing, which is almost the output of our function in terms of a nice basis of the inputs. This also generalizes quite well if our input distribution isn't Gaussian. This thing becomes what's called Wick chaos, which I do not have a scary looking picture of Wick, but trust me, he was also an intimidating looking guy. How do we do this? So it's a mathematical fact that the kth moment of these pre-activations is the sum of all tensor contractions among k Shin tensors. And then from the definition of cumulant, it follows that the kth cumulant is the sum of all connected contractions. So, okay, the variance, which is the second cumulant, there's Shin 1, you can only contract 2 Shin 1s in one way, and Shin 2, you can only contract 2 Shin 2s in one way, and then there's an infinite one, infinite power of the Shin 3, Shin 4, and so on. Yes? Oh, geez. I guess in this case, these like Shin, HE33 would be the second Hermite polynomial in direction 3, let's say. Yeah, I mean, that's a somewhat non-standard notation, but like this is giving the directions in which it's excited or whatever. Yeah.
I mean, generally you can have formulas for calculating the K cumulant, but it involves high-dimensional integrals over activation. You're going to sample the network.
No, we're not sampling. Sampling is sort of the naive thing. But yeah, I think the point is if you wanted to do it exactly, you would need to sum over all of the sets of neurons. We are like doing this in a completely different way. We're like, I can almost call it rearranging the sum. We are breaking each of those neurons into an expansion in terms of Hermites. Then we are summing together. Here's the first Hermite, first order Hermites. Here's the second order Hermites. Here's the third order Hermites, and then we're sort of dealing with each of those separately. So
different activation function will result in different expansion.
Well, it will resolve in like different coefficients in these Shins. Yeah. So the mathematical details will be different, but the moral story would be exactly the same.
Sorry, and the little z's are what exactly?
Little z, pre-activation. This is the pre-activation of the final neuron. So this is, if we get this guy's distribution, we win. He is almost Gaussian, so we just need to get like these tiny third, fourth, fifth cumulants. All right. Yeah. Go for it.
What is the stochasticity of your model coming from?
So like it is you're given a particular neural net with some particular weights. Right now, so far, we've mostly been thinking about ad initialization. I will have like 5 minutes talking about training, which is maybe not an appropriate ratio, but that's what we're going to do. And then, of course, if you want to figure out its average behavior, you can add an additional stochasticity and sample a bunch of inputs. We are not doing that. We're going to do something which is slightly more efficient, or possibly much more efficient in other regimes. Yeah, that's all the stochasticity.
But when you're talking about moments with this, like a sum distribution,
The input distribution. Yeah. So we're for the moment going to assume it's a known input distribution, and not only is it known, it's IID Gaussian, but that's not a particularly important assumption. All right. Thanks for keeping me honest. Yeah. So okay, we expand Shin. We expand this Z2 with all these glorious tensors. We sum up connected diagrams. Here's the diagrams for the second cumulant. There's obviously a scarier set of diagrams for the third, fourth, fifth cumulants. So okay, there's a whole power counting scheme telling you how much any given diagram should contribute and how hard it is to calculate any given diagram. So roughly, you can figure out each entry of each of Shin D is the input dimension to the negative D over 2. This sort of means each one is going to have Frobenius norm 1, so that checks out. And you can just multiply it out. So if you have L lines, I believe the each term is this big n0 to the minus L, but there will be n0 to the positive L terms if you assume they're independent, which is a solid assumption when you are at initialization. This diagram will then be pretty small, n0 to the minus L over 2. How long does it take to evaluate this diagram? First of all, does everyone roughly understand the power counting, even if you didn't follow every single where this came from? Okay, great. Yeah, long short, there's a power counting, and more edges equals less important. How long does it take to compute the diagram? Well, there's two stages. first you need to write down the shins, and then you need to do the contraction. Yeah.
Regarding the shins, I mean, I always assumed you were talking about distribution of random networks and their.
No, in some particular network.
It's a particular, so as with that, so you're assuming Gaussianity with respect to X, or some lower Hermite expansion with respect to the X?
There's two levels of randomness. You are randomly selecting a network, and then in order to calculate its average behavior, of course, you need to define a distribution over the input. Today I'm going to talk about Gaussianity for X, but that's not an important assumption. If you have some other favorite input distribution and you know its cumulants, that's fine too.
I'm mainly wondering how many Shin tensors you have to keep. How nonlinear is the output function?
You need an infinite number, but it turns out that the higher ones are less important because the diagrams have more edges. As you want to get more and more precise, you need more and more Shin tensors. Just like if you want to get more precise, you need more and more Feynman diagrams. Yeah.
So your weights are chosen from Gaussian distributions.
That's not particularly important, but yes, let's say they are.
And that's what's giving you the near Gaussianity.
No, that's completely unrelated. The near Gaussianity is just the sum of a lot of things.
Okay.
Yeah, so if they were, like PyTorch does it uniformly between -1 and 1, that would be fine as well.
It's because you're hidden layers really big.
Yes, yeah, yes, and also because the input layer is fairly big. Yes. Yeah, that's where the Gaussianity comes from. Yes, if you chose the weights, like everything I'm doing is completely independent of what distribution you're choosing the weights from. They can be bimodal or horrible student T distribution or whatever. Maybe not T distribution has long tails, but any reasonable distribution will be fine. And again, I'm not going to go into it too much today, but this works even after training, where they're obviously chosen from a ridiculously complicated distribution that results from training. Okay, so we're given a tensor contraction, and it turns out because of my original choice to make N0 way larger than anything else, the most expensive part of computing the tensor contraction is actually just writing down the tensors, because that's the only part that depends on N1 at all. The cost of computing a tensor diagram just ends up being N1 times N0 to the size of the largest individual tensor. These end up meaning that the hardest diagram with a given contribution to the answer is just two vertices with L edges between them. And even then, the tensor contraction is faster than sampling because it ends up being faster by a factor of N0. So in this case, we are sort of, I don't know, by the skin of our teeth, if you will, beating sampling. Here's a check mark in case you didn't believe we were winning before. I do want to talk a little bit about narrow hidden layers. The diagram story still goes through completely. You can still do the Hermite chaos thing. But obviously the power counting of what stuff is expensive is now completely different. And furthermore, these tensors are now sort of ridiculously low rank. By low rank, I mean they have these sparse decompositions, which means there's clever algorithms. So when the dust settles, we end up actually beating sampling by a pretty huge amount. So I had fun over the summer taking a 100 inputs, 100 hidden layer thing, and you can run it overnight using PyTorch, and then run 0.01 seconds using this algorithm using Mike level coding, which is arguably less optimized than PyTorch. And this algorithm will be more accurate. This requires that you spend an afternoon finding clever ways to contract these tensors, which depending on the person can be a fun or non-fun afternoon. I do also want to talk at least a little bit about trained MLPs. So some parts of this whole story are going to remain the same. The inputs to the hidden layer, I guess I was pretending to remain Gaussian. And it's still then the case that the Shin tensors perfectly encode the moments. There's no approximation in that. And if you're training using anything like neural tangent kernel, you can still ignore the really high Shins because you can't train those using neural tangent kernel. But some of what we were using are completely out the window. For instance, the input to the final layer is no longer going to be anything like a Gaussian, at least not in the worst case. So this whole perturbation expansion which again, statisticians call an Edgeworth expansion, doesn't work anymore. It's non-perturbative. Hold on. But that's okay. You can use a Borel-Rie summation. It's all fine. Borel-Rie summation is this horrible, to me, very unintuitive thing, but whatever, it works. And then a much, much worse issue, at least in terms of, affecting my sleep at night, is this power counting for which diagrams are important is now completely out the window. Right, like the Shin tensors can be arbitrary, and they can sort of have like conspiracy theories, conspiracies to make very large, complicated diagrams be large. Give a large final output. And in general, summing up arbitrary tensor contractions is what's called a Sharpe hard problem, which is even worse than NP hard. Luckily, there's a constraint on these tensors, which is that the sums of the squares of the entries can't be that big. We know because if they were, then the variance would be big. With this constraint, you can actually evaluate these tensor contractions fairly efficiently. You just need to spend a ridiculously large amount of effort coming up with clever algorithms, which we are almost done with convincing ourselves that these algorithms actually work. Okay, so for the one hidden layer MLP, at least trained with MTK, I think we are, we have mission accomplished. We are beating sampling by either a factor of the input or possibly much, much more than that when it's narrow. But there's still roughly an infinite number of additional problems we need to solve. I don't know if you know this, but a lot of modern neural networks have more than one hidden layer. So we're going to need to deal with that. We're going to need to deal with residual connections and attention, and one day we'll need to deal with chain of thought and all that stuff. Another unfortunate fact for physicists is that, depending on who you ask, fortunate fact for physicists is that they're trained with more complicated regimes than neural tangent kernel. So we're going to need to do mean field regimes, or maybe even more complicated than that, which are capable of training the larger shins. And finally, we're going to need to deal with more complicated input distributions. If your favorite input distribution is like, oh, it's not an IID Gaussian, it's like IID Bernoulli, then this logic will still go through. But if your favorite input distribution is like the actual input distribution that ChatGPT gets, which does not have a compact mathematical description, I think you're going to need genuinely new insights, which I do not have in order to answer these questions. Anyone have additional questions about what I did, or why I did it, or how I did it, or what I'll do next? Hakan, I guess first.
So once you get the components, say, how would that what would you do with them? Do you have them high dimensional components in function space, or?
So sorry, you had the cumulants of the final hidden layer. Okay, so I won't go into it too much. There's a whole cottage industry of reconstructing distributions of the cumulants. Sometimes it's doable, sometimes it isn't. If you're near Gaussian, it's absolutely doable. And the intuitive thing to do is just like say, okay, instead of being e to the x squared, it's e to the x squared plus a perturbation to you sort of like match it. And that'll work totally fine.
But a new network that learns would
Yeah.
start from Gaussian.
So this Edgeworth expansion doesn't converge, but it's still totally well defined. And you can again do Borel-Rie summation. I do not understand why this works, but empirically you can do this on your computer and it seems to give right answers. And yeah, I promise one day I will understand why this works, but I do.
Suppose you did this for a large network with a large hidden layer.
Sure.
What kind of insight can one get, let's say, for a typical problem like if you good diagnostic problem? What kind of results? Is it human readable?
Certainly not human readable.
So what do you do?
So actually, there's a few very interesting things. So it turns out that the only way that the answer can be far from Gaussian is if the Shin tensors have what's called a CR decomposition. There's a whole universe of cleverly decomposing tensors. Basically, if you have a So like if shin D can be written as a simple sum of tensor products. So first of all, I'm going to assert that these decompositions are fairly easy to find. Like just like singular value decompositions are fairly easy to find. And these are the only way that the result can be far from Gaussian. So like the shins do in a fairly straightforward way say, here's the interesting behavior. They actually let you extract, like here is a circuit, which is the equivalent of this function. Potentially fairly simple circuit, which is the equivalent of this function. So I believe that I've not actually done this on an MNIST classifier or anything like that, so I have no idea what the result will be. But yes, this can be used to extract, hey, here are our features, and we're doing a simple set of multiplication and addition on those features.
So perhaps related, if we go back to this question of like, can I find, can I guarantee that it will hit this line and then back output? Can you relate with this kind of shit manipulation back to event probabilities of very low events?
Well, so to me, it's most naturally to average estimation, but obviously you can put in another layer at the end which checks, was this thing bad? People say bad word, you need a classifier for your bad thing, which is a whole other issue. But assuming you have a classifier for your bad thing, you say the average value of the classifier. Yeah, any other questions? All right, that's for your attention.
We have lunch. We'll try to reconvene in about, say, 1 p.m. That's okay.